Hello, I'm Fei Chen from Kyoto University. I'm going to introduce our work, Dynamically Updating Event Representations for Temporal Relation Classification with Multi-Category Learning. So this is the content list. I first introduce some background of this task and some existing issues, the neural encoders for the NLP and the syntactic information. The second part is our main assumption of this model and the overall system framework. And the third part is the experimental result into dataset. We will give a summary at the end. So the first is the task definition of the temporal relation classification. Sorry. So first, we assume we already have the mention in the text. We have three types of mentions: event and time expressions, and the document creation time of news articles. So temporal relation classification is a pairwise classification task which is identify the temporal relation between a mention to another mention. There are four T-link categories. For example, from the event to the document creation time, E to D. From the event to time expressions, E to T. From event to another event, E to E. And the MET denote the relation between two matrix events. So we find two existing issues in this task. The first is, as we mentioned, we have four T-link categories, E to D and E to T and E to E and MET. So each category requires their independent features or attributes to construct the classifiers. So in the traditional setting, four categories had their own classifiers, which hinder from utilize all the data. So the second issue is the local pairwise setting that does not share information when even two pairs involving are common mentions. We can see example. We can see the first pair is a relation between the Hachimeru to the gonads. So the second pair is the Hachimeru to the Hojosu. So even they are involving with the same common mention Hachimeru. So in the pairwise setting, such information cannot be globally shared. So then I'm going to introduce some background of the neural NLP processing. So from the 2013, that there's an explosion of the neural networks, or we call deep learning. So a traditional way is we use a pre-trained distributed word embedding plus some neural networks such as the RSTM. So such methods dominate the NLP from 2013 until now. So, but something has changed from 2018. The transfer learning has become popular. The way is such as BERT, they adopt a unified deep transformer models. So they set up a training objectives, then train the model in a very large raw text. Then they use this pre-training the models to fine-tune on some specific tasks, like the supervised training model. So such transfer learning has dominant order NLP tasks in current days. So the second background is that syntactic information relay is featured this temporal relation classification task. This is our previous work in 2017, and the main idea is that we adopt the shortest dependency path between two mentions, then use this path as the input for the neural networks for the classification. So this work suggested the usefulness of the syntactic information. So after introduce several backgrounds, so we can make a comparison of the state-of-the-art models. The first model is our SDP RNN. So the encoder is the STM RNN, and we use the syntax tree, syntax plus tree. So it's then it doesn't use a global. It works as a local pairwise setting, so it's not global. It doesn't use doesn't cross the categories like the ET, E to D, and the E to E. So for each category, they have their independent classifier. So the second work is the fine-grained TRC. It's also it uses a Elmo encoder. It's a stronger version of LSTM, which is pre-trained. They didn't use their syntax. They didn't use the global inference. They didn't cross the categories. So the third work is the GC Air, which is a global context model. They use the LSTM as the encoder. They use the syntax shorted dependency parse as input. They infer the global inference. They somehow cross the categories because they use a single classifier for all T-links, but to use the category as a category information as a feature. So this work can be distinguished from the existing work is we use a stronger BERT model, a BERT encoder, but we didn't use the syntax information, which means our input is a sentential sequence. We use the global inference to share information across the pairs. We use the multitask learning to cross the multiple categories. This is the central assumption of our model. We can see our piece of example text in the news articles. So this news describes that FBI conduct a manhunt. Then the manhunt activities is continuing, and in this week, the FBI assigned more agents to search. So our assumption is that along the narrative order of the mentions, so we assume manhunt is the central event. In this case, manhunt is holding a include relation to the continuous. So manhunt includes continuous. So based on this early step pairs, we assume after predict the early pairs, so we can update the embedding of the central event manhunt, so which will benefit the prediction when manhunt link to the later step search. In this case, the later step, the link between the manhunt to the search it also have the same relation includes. So the idea is the early step updating will benefit the later step representations. So this is the overall system framework. So in the bottom, we input the original word sequence into a BERT encoder. Then we retrieve the representation of all the mentions located in this piece of text. So in this case, E1 is the representation of the main hunt. E2 is the continued T1 this week. E3 is the search. So we gradually update the representation of the central event main hunt along each time step. So in the early step, the main hunt will update the relation between main hunt to the DCT, between main hunt to the continue. Then in the later step, the updating will have the better representation, then improve their classification in the later steps. So overall, there's two main contributions of our work. The first is we use the global inference model to improve the representation of the central event. So the second contribution is on the top of this model, we use a multitask learning to overall the type of T-link categories, E2D and E2T and E2E. So the loss will be the sum of all three types or four types in the Japanese corpus. So we can see the result in the English dataset first. So as expected, our proposed models outperform all the existing tasks by a large margin. It was expected because we adopt a stronger BERT encoder. So we did the additional ablation test to evaluate the benefits from our two proposals. We can see the result in the bottom table. And by removing the global inference and the multi-category learning, we can see that our model dropped 3 points in the E2D and dropped 6 points in the E2T and dropped 6 points in the E2E categories. So which indicates that our two contributions make significant improvement for this task. So the second page is the Japanese corpus result. Yoshikawa-san's work is the state-of-art models, but it's a feature-based models we can find. So it was not surprising that our model outperformed this feature-based work. So in the ablation test, we can see that our model obtained a significant improvement, especially in the E2E and the MET. In the MET, our model obtained around 10-point improvements, which is huge. So we can make a summary that we propose a model with the strong BERT encoder, and we perform the multi-category learning over the E2D, E2T, and E2E categories. And we perform the global inference across the multiple T-links. Then our model outperformed the state-of-art model. Then the second point is the ablation test suggests that the effectiveness of our two main contributions, the multi-category learning and the global SEC inference. So as the future work, we plan to investigate some graph network for the global inference. So we assume our or SEC models is somehow a simplified version of the graph approach. Then this is some selected reference which is related to our related to this work. So that's all. Thank you for the listening.